Hi everyone. So this video is about discussing how to do inference with Dropout, and basically we will discuss what's known as the weight scaling inference rule and discuss the justification for this rule. So before, let's discuss what's the challenge, right? So why is inference a problem with Dropout? The problem is that you used all these many realizations of the network during training, right? So your cost function is actually the mean or the arithmetic mean or the expectation of the cost function across all possible realizations of the network or across all possible mask vectors, which we denoted as mu. Right? So to do that, basically the typical approach is to do what's known as Monte Carlo simulation, right? So to draw realizations and then take the average and hope that this is an unbiased estimate of the average, what you calculated through the empirical simulations, right? But that can be very costly because the number of these realizations is typically very large. So you would need to do a lot of you would need to draw a lot of realizations or a very expensive Monte Carlo simulation in order to have to start having what looks like an unbiased estimate, right? So instead, there is a very clever way to do inference with Dropout, which is basically what's used in the current implementations of the famous libraries like TensorFlow and PyTorch, and that's basically the weight scaling inference rule. And that rule relies on an approximation of the arithmetic mean by the geometric mean. Right, and there is basically a paper in ICLR 14 that introduced the concept and has a thorough analysis of where this approximation is coming from. In this video, we'll just discuss an overview and a very rough explanation of that approximation. So the geometric mean, basically, if you ignore the degenerate case that there is some probability of one of the classes, let's say it's a classification problem, one of the classes y has a probability 0 given the input vector, let's ignore that case. Then the geometric mean is basically given by what we call p tilde ensemble here. And it's the square root of 2 to the d, where d is the number of units that can be dropped, the number of input and hidden units. And you multiply by all possible mask vectors mu, probability of y, class y is the output given the input vector x, and drawing the realization of the network corresponding to the mask vector mu. So unlike the arithmetic mean, instead of summation you have multiplication, and instead of the division you have the root. And basically the idea is that if all the elements are like each other, if you sum them, then you get a multiple, and that's why you divide. If you multiply them, then you get a power, and that's why you take the root, right? And then you want this to be a probability, so basically we normalize over all possible classes. That's a very standard procedure. Now, what the weight scaling inference rule is that it approximates P ensemble by evaluating on just one model instead of drawing multiple realizations. And the idea is that I will take the original network and I will scale all the weights going from each unit by the probability of including that unit, right? So if the dropout probability is 0.8, that means I'm keeping that unit with probability 0.2. So I'll scale all the weights going out of this unit by probability 0.2. Right? So while during training, I'm drawing realizations where sometimes this unit is not there, during inference, every unit will always be there, but I will scale the weights. So after training, I have a parameter setting for the whole network. I will scale the weights going out of every unit by the probability of not dropping this unit. Okay? So if it's 0.5, then I scale all the weights coming out of that unit by 0.5. Now let's see what's the justification. So again, it's like we had rough approximations to justify or to interpret early stopping and to interpret L2. We'll have a similar thing here. So again, because it's very hard to analyze things with nonlinearities, we will ignore the effect of the hidden unit nonlinearities, but nevertheless we will not forget that we have done this, right? So we'll keep in mind what assumptions we have made. So the probability of having the output as class Y given a certain values for the input units, which we will call it V. Then basically it's given by the softmax of the output units, right? So the softmax of W transpose V, which is the linear transformation, W is the weight, plus the bias, and then you take the yth element of the softmax, which is basically the softmax corresponding to the yth unit. So this is the probability that the output class equals Y, right? So now instead of just the input, we are also given the mask vector. Let's call it D. It's a binary vector, right? And this is equal to softmax W transpose V element-wise product with D, right? So whenever D equals 0, you have a 0, right? Whenever D equal 1, you keep the corresponding element of V. So think of V as a vector, right? And then whenever the D equal 1, you keep the value. Whenever the D equals 0, you set the corresponding value to 0, okay? And then plus the bias, and then you take the yth element, right? Now P ensemble, which we just discussed, is equal P tilde ensemble over the sum of the probabilities. So this is just a normalization. Now let's take the P tilde ensemble, which is what we care about, of class Y. This is the geometric mean, square root 2 to the n, pi. Let's say that D is all the possible mask vectors all have equal probabilities, okay? So it's D, so I'll just multiply, okay, by D in 0, 1 to 2, 0, 1 to the n. So this is basically all the possible binary vectors of length n, probability of Y given V and D, right? Now, if it weren't the case that all the realizations or all the mask vectors have equal probabilities, then here I would also multiply by the probability of having this mask vector, right? But because we have all equal probabilities, so it's just a multiplication over all possible realizations of the conditional probability given the mask vector, okay? So we don't weight it because they all have the same probability. So basically, you have a square root of 2 to the n, pi over all possible realizations. The softmax, the conditional likelihood is given by the softmax of W transpose D element-wise multiplication with V plus the bias, and then you take the yth element. So if I do that, right, so it's as if I'm only, because I take the yth element of the softmax, it's as if I only take the weights connected to the yth output units. So this is the vector of W, this notation here, Y tilde, meaning that I take the row or column of W corresponding to the weights connected to the yth output unit, right? And then I multiply this, so I make this, if it's a column vector, I transpose so that it becomes a row vector, and I multiply it. So it's basically a dot product with D element-wise V, okay? Plus B times Y, so the bias corresponding to the yth output unit, okay? And so here, this is P tilde ensemble is proportional to this, right? Becomes proportional to the exponential, because softmax is basically proportional to exponentiating the value of the output unit, right? So here I have the P tilde ensemble becoming proportional to the square root of 2 to the n, and then the same thing, and instead of softmax, I have the exponential of these elements, right? So this is the exponential, and this is the vector of weights connected to the yth output unit, and this is basically a dot product between these two vectors, and the second vector is the mask vector element-wise with the input vector, okay? And then the bias corresponding to the yth output unit. Now, basically, the interesting observation is based on a very simple principle, is that if I multiply exponentials, it's as if I have exponential of the sum. If I take square root if I take the root of exponentials, it's as if I have exponential to 1 over the value of the root, right? So here I take the root of 2 to the n, then I have exponential 1 over 2 to the n. If I have multiplication of 2 to the n elements, then I have the exponential, the sum of these elements, right? Now, because I sum over all possible realizations, right? Every element in D will exist in exactly half of these elements, right? So the number of these elements is 2 to the n, right? And then every element of V will be preserved in exactly half of them, in 2 to the n divided by 2, right? So it's as if I have I have the weights connected to the yth output unit, dot product with the input vector V, and then this is multiplied by 2 to the n over 2. And because I have 1 over 2 to the n outside, then I just have 1 over half here, plus the bias connected to the yth output unit, right? So what we have here is that the conditional probability of class Y over the ensemble, given the input vector V, when all the realizations can be drawn with equal probability, when I have uniform distribution over the realizations, then the probability, the likelihood becomes equal to exponential, right? The soft max basically of half what I would get in the normal network, right? So I basically divided by half all the weights. Why are we doing this? Because if all realizations exist with the same probability, right, then every unit will be dropped by probability half. So this is the same as scaling all the weights going out of every unit by the dropout probability, right? So that simple analysis can be generalized to the case where you have non-uniform probabilities over or non-uniform dropout probabilities, or in general non-uniform probabilities over the different realizations of the network, right? So that was found experimentally to be, so although here we are ignoring the effect of nonlinearities, so it's not necessarily the case that this holds exactly in every network, it was found experimentally to be better than Monte Carlo approximations, even with large number of realizations using in the Monte Carlo approximation, but in most problems, right? So this is a problem dependent because here we ignore the effect of nonlinearity, so there might be cases where you still need the Monte Carlo approximation. But in general, this is the insight behind the weight scaling inference rule in Dropout. And this is basically what's enabling us to do in a computationally cheap way the average over the ensemble during inference when doing Dropout. Now, the last comment I want to say is that what do you need for Dropout in terms of memory cost is basically to store the mask vectors, which is order the number of units. So if the number of units n, then it will scale with the number of units. And also in terms of computation, to do the weight scaling inference rule, you need to do multiplications, a number of vector scaling that's equal to the number of units, because I scale the weights going out of every unit. So the computational cost will also scale linearly with the number of units, which can be expensive. And remember, the last time we've seen this was in backpropagation. The memory cost in backpropagation is also scaling with the number of units in the network. Thank you.